Welcome to the first in a series, CTSI Biostatistics series that's sponsored by the Clinical and Translational Science Institute and the Division of Biostatistics in the Department of Population Health. Whether you are wanting CME credit or not, please do sign in. And if you want CME credit, then of course you have to fill out the evaluation. And Tony is back there somewhere just outside, I think, and turn it into him. There are tables back there. So before I begin, I just want to sort of say that this particular lecture is more about concepts than anything else, okay? So I kind of want to strip down the example to very, very simple case so that we can focus in on what is it that we need from statistics in order to make some decisions in medicine. So the example is going to be a toy example, but I will use it to bring out lots of different concepts and terminology, and we'll review it at the end of the lecture. First of all, the speaker disclosure statement is required. Neither the sponsors nor I have any financial relationships to disclose, don't have any with any commercial entities. All right, so here's the outline. I'll introduce a data example, very simple, directly data, because I want to talk about data to decisions, right? And what do we need in between, conceptually, in order to make that transition? So these are some of the things that will be used on the way. Some design issues I'll talk about. Hypothesis formulation, what does that mean, and how do we set things up so that we can make decisions then at the end of the process. One important concept, perhaps the most important one here, is the study-to-study variation in whatever it is that you're measuring. Okay, and so we'll have to make clear distinctions between patient-to-patient variations and study-to-study variations. And hopefully I can get the point across. Testing of hypotheses. I said we'll formulate our decision problem in terms of hypotheses. And once you do that, then in light of the data, how can you make your decisions? Sometimes, or actually, from my perspective, always, confidence intervals are a good idea beyond your testing of hypotheses. And I'll try to say something about that. And then when we're done with this example, I'm going to go back and say, well, if you were to plan this study, what considerations might you have had? So considerations in planning a study is something that we will then end up with. All right, so here's the data scenario. Outcome is drop in blood pressure. Okay, so we're going to have a drug A, and the question is, does it reduce systolic blood pressure? 36 patients treated with drug A and 36 untreated patients. I hope lots of questions are popping up in your head right now about, I'm not telling you the whole story. That's deliberate because I want to think about what kinds of things you will need more than just these 4 lines that I have up here. But let's take a look at the data anyway. So on the left-hand side, with the lighter background, you have the drop in blood pressure for those that were not treated. There are 36 patients in each arm of the study. So we call these the 2 arms of the study. One is control on the left and treated on the right. Take a look at these numbers and see kind of what they look like. They are not all the same. They're quite variable. Perhaps you can see that on the right-hand side, the numbers are somewhat larger than on the left-hand side. These are drops in blood pressure. So if the drug is effective, we would see more higher numbers on the right-hand side, where that's the drug side, the treated side. Okay, this is the data. So now from this data, we want to make a decision about this drug. There are lots of things that we will sort out and try to make precise about what is that decision? Who is that decision about? Is it about these 72 individuals, or is it about something bigger than that? So that is first thing to think about, is that what decision you're going to make has nothing to do with these 72 people. They are telling us something, giving us some evidence about this drug, but the decision we want to make is about a much larger, what I will call a target population. So it's the hypothetical. If we were to use this drug to treat people, would we get an effective treatment? So I'm giving you a little bit more about the data now. So this is what the raw data, the 36 numbers on the left, the histogram looks like that, and 36 numbers on the right, the histogram looks like that. And this is what would happen. See, when you have data, it's very tempting to immediately go in and start playing with it and put it in Excel and take a look at, which is fine, okay? But to go from data to decisions, we're going to need lots of intermediate pieces, and I want to bring those out. So if you look at the mean on the left-hand side for the is 5.2, on the it's 11.1. Okay. Now, does this mean, should we say then that treatment is effective? You know, give us a bigger mean. What's wrong with that? Well, before we go to that, let's think about some design issues, first of all. We're not going to get into, there are further lectures coming in this series that will get at particular issues and discussions related to those issues, and I'll point out some of them. But generally speaking, you must have an extremely precise outcome definition. I didn't say very much at all. I just said drop in blood pressure, and I went on, right? Well, if you were actually conducting a study, you would need certainly a period of time, right? What is the dose of the drug? Is there compliance with the drug? How are you going to use that? Are you going to... So there are lots of issues about whether you're going to do an intent to treat analysis or as treated analysis. So there are lots of issues, detailed issues. I'm really not going into them, but I'm saying right now that you have to pay a lot of attention to the precise outcome definition. Okay, so you would need a time period, you would need a dose, you would probably need to know whether these are, what kind of patients they are. And you would assume they are hypertensives, perhaps of a certain age group, perhaps gender is involved. All of these definitions have to go into what we call a protocol much before you get to the data, right? So that's one thing. How will you recruit the patients? So that's what I was talking about, inclusion and exclusion criteria. Some disease conditions may exclude patients from getting in there. Inclusion of control group. Remember, at the beginning, I phrased the question by simply saying, does drug A reduce blood pressure, right? So you might say, well, all I need to do is study how much the drop in blood pressure is, and if it's positive, drug A produces blood pressure drop. But typically, or almost always, we have a control group, and the reason for that is, first of all, placebo effect. Okay? So we got to sort of make sure that we are showing the effectiveness beyond the placebo effect. And even in some cases, if that is not relevant, the placebo effect, you still need a control group because you need to have, under the same conditions, in the same environment, comparing the drug with no drug. So there are very, very few studies in which you will not have a control group. So that's a very important design aspect. Assignment to a treatment arm. So how will you assign treatment and control? So that's typically randomization is used, But what kind of randomization? Are you going to assign in matched pairs? Why would that be relevant? Well, you might say that it's not really meaningful to compare a 25-year-old hypertensive with a 60-year-old hypertensive. And so you may want to get pairs of patients that are matched on age and then randomize one to one treatment, the other to the other treatment. So paired randomization is also very important, and its analysis is different. In fact, one of the lectures that's coming up in the series is focusing on these. I believe it's the one next month. The next month is, equivalence. So there is, I think it's the month after that. So it would be January, or so. So there is, okay. Now, what I'm going to show you today, at least the data that I showed you, was collected in a way that did not use matched pairs. Okay, so they were independent samples, and we simply are using randomization to balance. What does that mean? That means that I'm not going to get younger people in one group and older people in the other group. That would be very unusual if I'm flipping coins to decide who goes into what arm. Okay? And that's one of the advantages of randomization. Overall, it'll get you balance. But that may not be relevant. You may want to match, because if you match, then you get sometimes a lot more precision in the measurement that you're looking for. So there are many reasons to match. But my example today it does not use matching. It's just simply what we call independent samples, control and treated arms. So the randomization was not done by pairs. So randomization allows quantification of decision uncertainties. So everything that I'm going to talk about has to do, if you don't have randomization, then the rest of the lecture is useless. You might as well walk out right now. So without randomization, you really cannot quantify decision uncertainties. What do I mean by that? Patients are variable, and therefore just taking 72 patients is not going to tell us everything about the entire target population. So how much is that variation? So the decision you make is going to be subject to error after all. And that's what I mean by this decision uncertainty. So we want to quantify that decision uncertainty, make sure it's small, and actually give a number or two or three that tell us what the decision uncertainty is. And in order to do that, we have to have randomization, because only then do our techniques that are mathematical can actually quantify. Okay? So randomization is a very important aspect of these experiments. So let's see. So decision problem formulation then, back to saying, so we have to clarify exactly what we mean, and we typically pose this experiment into opposing possibilities. Okay? And so we have two statements, and we're going to then prove one of them and disprove the other. You can also think about the court of law, and that's a very good parallel to keep in mind. The accused is innocent and the accused is guilty are the two statements that are opposing. And here we would have drug A reduces systolic blood pressure. Drug A does not reduce systolic blood pressure. But we actually changed that a little bit, and we said, no, we're going to compare it to placebo. So drug A reduces systolic blood pressure more than does placebo, right? And that's not the case, is the last statement here. So those two are opposing statements. Now, in terms of the court of law, you see that are the two statements symmetric? Think about this. Accused is innocent, accused is guilty. Do we go into the court saying, oh, it's 50-50, guilty or not guilty? We don't do that. What we do is we assume innocence until proven guilty. So there is the notion of burden of proof, and that notion applies here also. The burden of proof here is on what is called the research hypothesis, which would be this: drug A reduces systolic blood pressure more than does placebo, right? So that would be your so you're the prosecutor and you're trying to prove this. So what you're trying to disprove then is called the null hypothesis. Okay, so that's the opposite. So the burden of proof is not on the null. The burden of proof is on the alternative hypothesis or the research hypothesis. These are the two words that are used to describe that. And that is, okay, so there's what I just already said. So the researcher is acting like a prosecutor, and research hypothesis is like accused is guilty. Okay? So I think I already said all of this that is on this slide. Now, so why do we need, this is all fine up to now, so but I didn't say anything about statistics and chances and so on. How does that come into this framework? Why do we need statistical reasoning? Because first of all, we're generalizing from patients in the study to a much larger target population. And so there is going to be uncertainty in that. So that means statistical techniques are needed. Repeatability. So this is, of course, a great principle of science that whatever experiments you do, you should describe them properly, and somebody else should be able to replicate them, right? Now, what about that? So we might want to think about what would happen if someone else also did this kind of a study. Okay, again, 36 patients in each of the two arms, and what would that be? What would that look like? So active, deliberate randomization achieves conceptual equivalence of patient groups in repeated studies. Think about that. If you chose any way other than randomization, it would be very difficult to say that a study is being repeated. Because if it depended on how you choose, and you use some subjectivity in choosing or assigning patients to the two arms, then it would be very difficult to say that someone else could actually replicate your experiment. But if you're actively and deliberately randomizing, someone else could do that too, actively and deliberately randomize, and therefore get a comparable study. Okay, so these are the reasons, again, why we want to be thinking statistically. So, variability. We have, and I've been saying this, I said that right at the outset in my outline, that we need to focus on two kinds of variability. So patient-to-patient variation in response. You saw that in the data, and I'll put that data up again. And different drops in blood pressure were different. They ranged from, I don't know, -2 to 18 or something like that. Okay? So that's patient-to-patient variation. Well, that's good. That is at the basis of all variation, is the patient-to-patient variation. If every patient gave the same response, then this would be easy. We wouldn't need statistics at all. But that's not the case. So that's fine. But in order to think about our decisions, what we need to do is translate that patient-to-patient variation to study-to-study variation. In other words, remember this repeatability idea. You're going to do this experiment once, and then someone else is going to do similar kind of randomization and so on, and they are not going to get the same drops in blood pressure that you're seeing. And so therefore, the question is, how far will their result be from yours? That's a completely different kind of variation. And that is the one that really is going to be important for the considerations we will go through in the next few minutes. Okay. Now, the second, this one, study to study, does have a mathematical relation to the first. Okay. And so we can actually derive a formula for these things, but that's not what we're focusing on today. I think you need to understand that patient-to-patient variation then translates into study-to-study variation. Okay, and as a researcher, you should really think more about the study-to-study variation, and we'll give these things names in a minute or two. So here's back to the sample. So the particular sample that I showed you, one mean was 5.2, the other mean was 11.1. And if I take the difference, 11 minus that, then I get 5.9. Okay? So we've got 5.9 as the difference. And then the question is going to be, well, is this difference good enough? What does it mean? What does this 5.9 mean? Should we then say that we have disproved the null hypothesis? Remember, the null hypothesis that this drug is not any better than the placebo. And now we got 5.9. Well, then now comes that study-to-study variation idea. It's not enough to just get a positive number. And I'll show you why, in a minute. But it needs to be big enough so that it's past the study-to-study variation, if you will. Okay? Or if someone else did this kind of a study, and they are just as likely to get minus 5.9, right, then this is not a good 5.9. This 5.9 hasn't proved anything. So it's not enough to just look at this, but to see the study-to-study variation. Let me see if I can show you that. Bear with me for a second here. No, not this. And so I want to show you what happens. This is the picture up here. See, it has a mean about 11. So remember our mean was 11 in the data for the drug A patients. The drop in blood pressure had a mean of 11 point something. So this is, and I matched sort of the standard deviation approximately to 5. And in that case, this distribution would kind of represent the target population, if that was the true story. It isn't, we don't know that yet. But let's suppose that that is the case. Now, what I'm going to do is I'm going to take a sample of size 30. This particular applet didn't give me 36, so I couldn't quite get 36, but 30 is close enough. So there's a sample. So there's a study like yours, okay? And those are the individual patients' measurements. See, they come close to 0. Some of them are up in the 20, 18. We got those numbers like that, right? So this is like one story. And you see this little dot here? That's the average of this particular study, okay? That was, I think, 11 point something for us, 11.1. All right? So now what we want to do is I take another sample. A different sample here. It's not the same. And it turned out that that mean was pretty close to the first one. You don't see it. You just see it stacked on it. Let's do it one more time. Now you see this mean right here? It was a different mean, correct? And one more time, okay? So every study is giving us a different mean. Let's walk this thing through and see what happens. As you get going, you get different studies, all right? And it's filling in. Different studies are giving you different means. Study averages. The 5 point, it's changing. Let's not, this is getting boring. Let's just finish it up. It'll do it faster this way. And so I'm doing 500 studies just to see what the study-to-study variation is. What do you see? The most important thing to see here is the spread of these numbers is much smaller than the spread up here. And this is what I've been talking about, is to focus from this patient-to-patient variation to study-to-study variation. Okay, now it depends on what it is you're measuring. What is it? This is the mean. Now you may have something different in mind, and we actually have a difference in means that we were wanting to do. Okay, so let's see if we can do that. Well, I think it's enough of this for now, but I'll come back and show you some other simulations like that. So here's the formula. don't worry about the formula, really. I mean, what is more important is the word or the phrase, standard error. Okay? So we're talking about the standard error of the statistic. What is the statistic? The difference in the means. So we got 5.9, right? So that 5.9, how much standard error does it have? What is the variation from study to study in that? That will be given by the standard error, different from standard deviation, which speaks to patient variation. So, let's try and actually I didn't show you that. I'll show you the actual value of this in a few minutes, and then when we quantify this a little bit better. Now, so what is it that we have this data, and we have set up our hypothesis. Now let's kind of make it a little bit more precise. So this symbol mu is used to denote not the mean of the patients in the sample, but the target population. Okay? Patients in the sample, we know what the value is, right? The patients in the sample, the treated ones had 11.1 as the average. So that's a number. This is not that. This is if you were to treat everyone in the target population with this drug similarly, what would be their average drop in blood pressure? That's mu with mu treated. And then this is the mu under placebo. So the null hypothesis says that there is no difference in these two mu's, right? This is what we would say. And then the mean reduction. So what we want to do is we want to disprove this null hypothesis. So then we will have proven our alternative hypothesis. Now the alternative hypothesis is that this treated mean is bigger than the placebo mean. So I didn't write it down here. But so here it is. So our mean turned out to be 5.9, right? This, notice I didn't say mu treated here. I said mean treated. This is for the patient, 36 patients. It's very different, right? It's going to be different in a different study. So that difference is 5.9. Have we disproved the null hypothesis? No, because there is study-to-study variation, and we know that the standard deviation of the treated group was this, standard deviation of the placebo group was this, and this 1.24 is that study-to-study variation in this 5.9. Is that okay? I showed you the formula, right? So I just plugged these numbers into the formula to get it. It's not important. The calculation is not important, but the concept is important. Standard error of the mean difference. Standard error, which is the study-to-study variation, depends on what it is you're computing out of the study. Okay? Here we were computing this particular mean difference. So that's its standard deviation. Now, maybe we can do one more simulation here. To see how that might go. So what is this now that I've set up here? Under our null hypothesis, this is simulation. This is if the null hypothesis is true. The null hypothesis says that, so you don't see two different curves. You just see one curve because they are superimposed on top of each other. If they both have the same mean, we're saying, and we're saying they have the same standard deviation or roughly the same, then you get this. Now I'm going to take a sample of size 30 from the controls and 30 from the treateds, okay? And let's do that by stepping here one time. And okay, so the two different colors are being used here to denote the two arms of the study. Okay, but they are under the null hypothesis, so there is no difference in the target population. If that were the case, you would get this, and then this is the number. It's pretty close to 0. By the way, this axis is not on the same as this axis because this is standardized. Okay, that's the only difference. So what they did was take the difference in the means and divide by the standard error. Okay, that way it gets it onto a z-axis, or they've marked this as a t-distribution, but that's a minor point for our discussion today. So that's the number that resulted out of this particular study. Okay, if we did it again, and you get a different sample. See, that's changed, right? And then you can see that it's over here. And one more time will give us a different sample yet. And let's start walking this through. And you can see that these are various different things that are happening, right? In other words, different studies can result in various different values of the statistic. Let's see if we can just finish it quickly. So I don't know if you've been keeping an eye on this shaded area here that they had. Let's rescale it. So if this null hypothesis is true, then all your study statistics are going to have this kind of a variation. This gives us a clue as to how to control the probability of making an error and concluding that the drug is effective when it isn't. Because this is the scenario that the drug is not effective, right? So in repeated studies under this assumption, you would get values like this. So you want a value somewhere out here is what you want. If you only decide that the drug is effective if this statistic comes out into this tail, then you will have controlled the probability of an error, because then what happens is that a study under the null hypothesis would not come out there, would not be very likely to come out there. Do some studies come out there? Yes, sure. Okay? So we are making decisions in the face of uncertainty, and so we accept the fact that some studies like ours are going to get the wrong conclusion. All we can do is control the chance of making a wrong decision. So, okay, let's then try to see how that goes. This is, by the way, this is the website where for that simulation applet that I used to show you. Both of those are at that website. Okay. So here's the decision. See, from that simulation picture, you saw that the cutoff was somewhere around 2, right? It's actually right about at 2. And what is this? This is the distribution that we saw simulated, right? It's the statistic that you calculate. Now, here I'm back on the difference axis. So I'm not standardizing here, okay? So now, this distribution does not have a standard deviation of 5. It has that 1.24 standard error is the standard distribution, standard deviation of this one, the spread. And the tail area here, I make that to be 0.05. This is a standard number that people use, is 5% error. Okay? Now what kind of error? I'll make that clear in a minute or so. So in order to make this error small, your cutoff ought to be something here. It's around 2. But the idea is we want to control that particular probability. So most of the studies, if the null hypothesis is true, will come out here. And you will not incorrectly say that the drug is effective. Okay? Now, there is a 5% chance that you will incorrectly say that the drug is effective. That's an error probability that we live with. Okay? So, to make this precise, rejecting the null hypothesis when it is true is called the type 1 error. You can see right away that there are 2 kinds of errors, right? You can either let an innocent man go free, right? Innocent man to jail, or send or let a guilty person go free. Those are the 2 kinds of errors. So we are going to get those 2 kinds of errors. This type 1 error is sending an innocent man to jail. And that we consider to be the more serious error, and we control it, right? In the court of law, we want to make sure, that is why the burden of proof is on the prosecutor and not on the accused. Same thing here. The burden of proof is on the alternative hypothesis, not on the null. The null hypothesis is something you will take unless you have evidence for the alternative. And so if the null is true, you want the probability of rejecting it to be pretty small. And that's what this alpha of 0.05 tries to ensure. Now, of course, how to choose that alpha? Well, it's become pretty much standard to use an alpha of 0.05, but there isn't really very good reason for that. 0.01 is perhaps, it depends on what are the consequences of this bad decision. And that's really what would decide what this alpha ought to be. So the mean difference in the study is 5.9, right? And so we saw that the cutoff was 2. So we would conclude now, see, we have a decision from the data that we collected. If we collected it with correct randomization and so on, we are now able to say, okay, we reject this null hypothesis, and we conclude that the drug is indeed effective in reducing blood pressure. Now, so if we have rejected the type, so now what we do, we declared the accused guilty, right? So now we could have only sent this person to jail when they were innocent. We could not have made the other kind of error. So after a decision is made, you're only exposed to one kind of error. Before the decision is made, there are 2 possible kinds of error. So what happens here is that, okay, you have rejected the null hypothesis, but we controlled the type 1 error probability fairly well, down to 5%, so we feel confident about our decision, and that's how the burden of proof is answered now, right? With that quantification of 0.05, we have answered. And so this is the idea. Now, decision can be made at any set level of alpha. So if there was, suppose we were not happy with 0.05 as the error probability, wanted it down to 0.01. Well, going back to that normal distribution, I can compute a different cutoff. It'll be somewhere around 2.5 or something like that, okay? So lots of programs that'll easily let you compute those things. So, so we can, now, as a reporting device, what we do often is rather than set an alpha, we say, all right, can I give a number out of my study that will then allow anyone else that's reading this study to make their decision at whatever alpha they want to set it at, okay? Now, there is such a number that you can give out of your study, and that is called the p-value, and it's only a reporting device. And I want to talk about that just a little bit. What is the p-value here? P-value for the case of 5.9, we saw a difference of 5.9, is very, very small. You know what that is? I'm not going to put up the picture again. I'll put up several other pictures like it in a minute or two. But that normal distribution with the tail that was colored red, that cutoff was at 2. And the middle point was at 0. So 5 and 6, 5.9, was not even on the scale, or not even on the graph at all. So you can see that that tail area beyond 5.9 would be very, very tiny, right? And when I made the calculation, that's the number that I get. Why is that important? It's really not important as a number itself, okay? And it is not the probability of the null hypothesis being true. That's not, never interpret that way. It's simply a reporting device. It says if I give everyone this number, I don't have to tell them necessarily this 5.9 that is sitting up there and the standard error and the whole bit. I can just tell them that this is the p-value that resulted out of my study. Why is it good? Well, someone else looks at it and says, oh, we should make this decision at probability of type 1 error of 5%. Well, this is clearly then saying that the drug is effective. Okay? 1%, yes, still. 0.1% alpha control, yes, still this experiment says the same decision. You see what I'm saying? All right, so I'll show you a picture on the next slide, and that'll probably make it clear. If the mean difference is something else, 1.8, then the p-value is 0.073. I made this calculus. I pretended that the mean difference is 1.8, and I get this. If I report this, then people know that if you want to control alpha at 5%, then this study does not prove the alternative. Okay? However, if you're willing to accept a 10% type 1 error rate, then this study will result in rejecting the null hypothesis. Okay? So it all depends on how much type 1 error probability you're satisfied with. So smaller the p-value, stronger is the evidence against the null. Right? It kind of goes, you're looking for small numbers, then it's stronger evidence. However, this is the most important line on this slide. P-value is not the probability that the null hypothesis. This is how people try to interpret it, and it's just a totally incorrect thing to say. Okay? Smaller the p-value, stronger the evidence. Correct statement to say. Okay? But p-value is only a reporting device. That's what you should keep. Don't try to interpret the actual number any more than that. It's just meant to convey what came out of your experiment. So here's here are a couple of cases to show you the p-value. So if the mean difference were 2.5, then you would put this at 2.5 and calculate this tail area, and I colored it yellow, not red. Okay, the red was the one that corresponded to a fixed alpha level, right? And this time I just drew that red line. So the area to the right of this red line is 5%. Area to the right of this experimental outcome is 2.2%. You see? So if the p-value is smaller than 0.05, you are going to reject the null at alpha equal to 0.05. Okay, so the p-value tells you that. If mean difference was 1.5, the p-value is 11%, and you see this is where the experimental result came out. This would have been your cutoff, right? And so you don't have to know what this difference is. You can only look at the p-value and make your decision at any alpha level. Okay, so that's the translation. That's the reporting advantage of the p-value. Okay, so now back to the data again. And now we say, all right, well, this is fine. We had this strong p-value, or very small p-value, strong evidence against the null hypothesis. So we will conclude with this that that drug A is better than placebo, right? But it does not tell you how much better. And don't look to the p-value to tell you that, okay? That doesn't mean anything. Remember, p-value is only for making one decision one time, and that's it. Then you throw it away. And then, so the question is, how much better is it, right? How much better is this drug than placebo? 5.9 might be your answer, right? But is that the correct answer? Remember, there is study-to-study variation in this 5.9. So you can't say necessarily 5.9. You have to be a little uncertain about what that is, because if someone else did a study, they're going to get a different value. How much different value will they get? That's what we want to find out. So let's see. So let's go to this website again. Let's see. Here it is. So now what I've done here is kind of have this 5. I set the value at 5. It was 5.9 for opposites. Let's pretend that the true value is 5, right? And you're going to do these studies over and over again. What I'm going to do is I'm going to do something here's your 5.9. We want plus minus some error. See, that's what we want to do, right? The election season just ended, and you heard about the errors. So, it's a very simple thing. My standard error was 1.24, if you remember. So if you multiply 1.24 by roughly 2, you get 95% probability in the middle of a normal distribution. Okay? So 5.9 plus minus twice the standard error. That's it. And I'll make two limits, and those are called confidence intervals. That's called a confidence interval. So let's pretend and take a sample. Here's a sample, right? And then you see this? That's a confidence interval, this blue line. And that happened to be the mean for that particular sample, but the endpoints are these two. Okay? Let's do one more. And you get a different line, right? And you do a third one, you get a different line, different segment. It moves a little bit. Oops, that one, notice what happened. It missed. It is also a 95% confidence interval, but that particular sample missed the true value. Is that okay? Let's run all of these. These are, I think, 100 of them. Right? And now, actually, what is it? 1, 2, 3, 4, 5, 6, 7 red ones in there. That's not bad. We've set the error rate at 5. We're making 95% confidence interval. That means that, what does it actually mean? The one you made could have been this one, right? You wouldn't know. It doesn't come colored, so you're not going to know that. It's just that you reached into this bag and drew out your confidence interval. But that bag was very good. It had 95% good ones. That's what a confidence interval means. So you construct the confidence interval with a formula and roughly what I told you about. But once again, we're not focusing on the formulas today. And that's the idea of a confidence interval. So we would have, did I ever compute it? Oh yeah, I did compute it. Here it is. 3.47 to 8.33. Now you can say that, this drug will, with 95% confidence, now unfortunately we cannot say 95% probability, okay, because the true value is either in here or not in here. There is no probability attached to it. But what we can say is we used a very good procedure. That's the bottom line. This interval was made by using a procedure that had 95% chance of capturing the true value. So that's the idea of confidence intervals, and it really is something you should always do. No question. Never stop with just testing and computing p-values, because that, as a physician, tells you nothing. Nothing more. You want to know how much. How much does this, what is the quantification of this effect that this drug is supposed to have? I mean, that's the important part. 1.96, that comes from the normal table. So in the normal distribution, from minus 1.96 to plus 1.96, there is 95% probability. Oh, okay. So if you choose the 95%, so you first choose the confidence level. We chose it to be 95%. This is typically people use 95%. Then that number is automatically decided, because you draw the normal curve and say, what is the cutoff that gives me 95% area in the middle? And that number happens to be 1.96. Okay? So it's roughly 2. I mean, if you can remember it as 2. So that's why I said plus minus 2 standard errors. See, this is roughly 2, and that's the standard error. You compute that number, that's 2.43. You add 5.9 to it, subtract that number, and you get these two. That's how each of those blue intervals were made that I showed you. Even the red ones were made the same way. They just didn't happen to capture the correct mean. And that's going to happen. Okay. Now, let's go back to the testing scenario, because I do want to talk about the type 2 error. In other words, this is a 2 by 2 sort of a truth table. The columns represent what might be the case. Null hypothesis may be true or may be false. And then your decision is represented by the rows. So you either reject the null hypothesis because you got a big enough value, or you don't reject the null hypothesis. We typically don't accept the null hypothesis. Accept is a pretty strong way to state it. We're really only saying fail to reject the null. Roughly the same. I mean, you don't go about saying, the accused was proved innocent. Okay? Not found guilty. That's all. So it's a similar thing. Now, of course, these two, the red or the pink squares are where the errors are. Right? The type 1 error we talked about quite a bit already. And the type 2 error is when the null hypothesis is false, but you don't reject it. Now, see, this is not good either, right? In other words, if your drug is in fact effective, you want to be able to say it is. You don't want to say that, because you're not making that drug available to patients who might need it. So let's see how to do that. So in planning a study, this is actually sort of more important, this type 2 error business. And typically we talk in terms of power rather than type 2 error, and you'll see why in a minute. That's when it is important. So what you want to do is you want to set the probability of type 1 error, let's say at 0.05. And then we also want a small probability of accepting the null hypothesis or not rejecting it if it is false. Equivalently, we want a large probability of rejecting the null hypothesis if it is false. So think about that. I think that's an easier thing to think about, because you're always thinking about rejecting the null. Okay? So for type 1 error, it's rejecting the null when it is true. Power is rejecting the null when null is false. This is something you want to do. So you want power to be high, not small. Does that make sense? I'll show you a picture or two, and that might help. But power or probability of type 2 error, either one, depends on effect size. It's no more. See, the null hypothesis just said 0, right? The research hypothesis doesn't say what the number is. So you can't calculate a single probability for it. You have to calculate the power against a particular effect size. All right? So let's see how that is done. So here are a couple of pictures. On the left-hand side, the effect size is 4. What are the two curves that I'm drawing? They represent study-to-study variation in the mean difference. If someone else did the same kind of study, what would happen? The blue curve on the left is under the null hypothesis. Notice it's centered at 0, isn't it? Okay? Now, if you look here in this tail, that's your alpha of 0.05, the red piece there under the blue curve. Okay? Now, the red curve is centered at 4, which is the effect size against which we are computing the power. So this is a scenario. What if? Okay? If the effect size is 4, what would be your probability of then saying that the drug is good, right? Of rejecting the null. That is represented by the shaded blue area. Okay? And it happens to be 94%. So now it will depend on this. Look what happens here. This is done under 3. Effect size is 3. Notice what's going to happen to the power. It's going to go down, isn't it? Because the two curves are coming closer together. Okay? So the area is the same. The part of the axis is the same from this point on. But the curve now has shifted to where it's centered at 3 rather than at 4. So as you decrease the effect size, your power goes down. you're trying to detect a small difference. It's harder. Okay, so it's intuitively it sort of agrees. It's not counterintuitive at all, but you got to kind of think in terms of these pictures a little bit to get the concept right. Okay. So now, what can we do? Well, what if I'm not happy with this situation? Let's say this 0.78. I don't like this, and I want a higher power at effect size of 3. This is study planning considerations. This is not after the fact. So this kind of reasoning should have happened way before you ever took the samples, right? And you say, well, suppose I'm fixed on this effect size of 3. I want to be able to detect and be able to reject the null hypothesis if the true drop in blood pressure is 3 millimeters of mercury. Okay? You might say that's pretty small, but this whole lecture has not been about realistic numbers, just concepts. Okay. So if you want that 3, but you want a higher power, what do you think you can do? Increase the sample size. Collect more information, right? That would be the intuitive thing to say. What does it mean in terms of these pictures? So I quadrupled the sample size, and notice what happened. The taller ones are with the higher sample size. So instead of 36 in each arm of the study, what is 144? Is 4 times that? Yeah. So that's what the sample size is for this. So notice what happens. Now these two get skinnier, and you win in 2 ways. This number right here, see, is not a 2 anymore. The cutoff has moved closer to 0. You see that? It used to be a 2 under this. By the way, the ones that are more spread out are the 36 sample size story. Okay? So as you increase the sample size, this distribution got skinnier. Distribution of study to study variation got skinnier, and therefore it moved 2 things. It moved this to the left, okay, which gives you a bigger axis here, and it also moved more of the air because this curve got skinny too. All right? And then that power got up to 0.99. So there is a clear relationship between power and sample size. So in planning your study, that's what you need to do, is to try to figure out what is your effect size, what is your study supposed to detect, right? And then be able to calculate the appropriate sample size that gives you a good chance of detecting. 0.99 would be an excellent chance of detecting an effect size of 3. And of course, if the effect size is 4, then you would get even a bigger number for power, right? Okay, so these are the kinds of statistical considerations that go into planning your study. So I think I have managed to talk about all the concepts that I wanted to, and this is a listing of all the words that I think I've used: treatment arm, control arm, randomization, target population, study, sample, null hypothesis, alternative or research hypothesis, standard deviation, patient-to-patient variation, standard error, study-to-study variation. Type 1 error, alpha is the probability of type 1 error, p-value, type 2 error, power, effect size, sample size, confidence interval. A lot of ground to have covered. Couple of things. The CTSI supports education, collaboration and research in clinical and translational science, and the Biostatistics Consulting Service is also there to help you with all the technicalities that go into this, right? So we have skipped all the technicalities today because if you go to the consulting center, they might help you do the numbers right, okay? Now, do remember to sign up. Even if you don't want credit, just sign in. And if you want CME credit, of course, fill out the evaluation. And you're welcome to fill out the evaluation even if you don't want CME credit. Okay, that's all I have to say. questions?